better. Our next speaker is Dorota Kruzynska. She is a PhD student in the Astronomical Observatory of the Adam Mickiewicz University in Poland, where she also obtained her bachelor's and master's degrees in astronomy. Her talk is titled Trajectory Predictions of Space Debris Moving on Highly Elliptical Orbits.
Does this work here?
Yeah, that should work. Should we?
Yeah. Okay. So good morning, everyone. My name is Dorota Kruzynska, and I'm here today with also one of my co-author, Professor Edwin Vnuk, and we'd like to present our work about trajectory prediction of space debris moving on highly elliptical orbits. So as a beginning, we should describe the highly elliptical orbit. So these are orbits with eccentricity, let's say, more than 0.1. And the most important is that objects crossing the LEO, MEO, and GEO regions with different velocity. Here is a table with the same altitude of perigee, about 700 kilometers, and different eccentricity values, and the different semi-major axes. And we can see that the period changes from hours to even 2 days time span, and the velocity in perigee, for example, for 0.7 eccentricity, reaches even 10 kilometers per second. Okay, so in the NORAD-TLE satellite catalog, we can find about 15,000 objects, where most of them are in LEO region. This is this high peak. But if we select the objects with eccentricity above 0.4 and the semi-major axis above 9,000 kilometers, we can see that there are also a lot of objects there. And also the eccentricity, we can see that also most of objects has the eccentricity nearly zero, so they are nearly circular orbits. But if we cut them here or take the eccentricity value above 0.4, there are still a lot of objects there. And the main peak we can see about the eccentricity value 0.72. There are two aspects of orbital evolution of space debris. First is the long-term evolution of individual objects or a given group of objects. And we can calculate for it for years or 10 of years time span, usually to get general characteristics. For example, the total number of objects or spatial distribution of density, and the use of the relatively simple theory of motion for statistical analysis of future orbit or a large number of objects. So it's like a cloud of particles. And we can use the analytical and semi-analytical methods or numerical integration with simple force model. For short-term orbital evolution of space debris, it is good to calculate the future position and velocity vectors of individual objects, and they are calculated for a few days or a few weeks, and alternatively a few months time span, and they are calculated with high accuracy of predicted position. We can use numerical methods for very high precision, or analytical methods. They are useful but limited accuracy and difficult in some applications, for example, when we've got high eccentricity value, resonances, and they are useful in collision avoidance or laser debris removal. In Poznań, we developed, as we call it, Poznań orbit propagator, and it consists of two parts: short-term orbit propagator, and its stop it's in two versions, analytical, that use the analytical and semi-analytical theories of satellite motion, and the numerical, based on numerical integration of equation of motion, and the long-term orbit propagator, which is based on the numerical methods and semi-analytical methods. So the top is the analytical version is used for predict position. Predicted position are calculated with the use of the second-order analytical theory. They are not sensitive to singularities for small eccentricities and small inclinations. The numerical version, predicted position are calculated using numerical integration of equation of motion. And in both options, the following forces are taken into account: the geopotential of arbitrary degree and other spherical harmonics, gravity influence of the moon and sun, so these are the lunisolar effects, the solar radiation pressure, and drag coefficient, the atmospheric drag. This propagator is based on the second order of analytical theory in the sense of Horley canonical transformation. The applied theory is non-singular for small eccentricity, and direct transformation from oscillating to mean elements and inverse transformation for mean to oscillating elements are realized with the use of Mersmann version of canonical transformation and are calculated with the same high-level accuracy. So as we can see here, this is the initial coordinates from epoch T0 and then for epoch T. We are using the double averaged from oscillating elements to the mean elements, then adding secular perturbation and using invert transformation from mean elements to oscillating elements. And this is the analytical, using the analytical theory, or we can just jump from one to another using the numerical integration. And perturbing force, perturbing function consists here in geopotential from the Kala eccentricity function, which is one of here. And in lunisolar perturbation, it consists of Hansen coefficients, which is here. And the Hansen coefficients, the Kala eccentricity function is related to Hansen coefficient by this relation. And the Hansen function is calculating using this, we're using the Tisserand method, which E is given by this equation. And here also is the JL, they are Bessel function of the first kind. The Bessel function has a stability problem in calculation for high value of eccentricity and high indexes. At the beginning, we have to calculate the J0 by directly from the definition for small values of key E, if it's less than 20. But if it's higher, then we use the Jacobi asymptotic formula for high values. All other Bessel functions are simply calculated using recursive relation. Okay, so for different, we've got here two plots. As we can remember, here is the equation, the G function, Kaula G function, and the Hansen coefficient. For different eccentricity value, we can calculate this. As we can see here, for nearly circular orbits, the value of Hansen function is about 10 to minus 90, and if the eccentricity increase, this value increased to 10 to 60, 10 to 70. So there's a big problem with accuracy, because this is really low value and this is very, very high value. So in computer, this makes quite big problems. And here, the second plot, we can see also the G and Hansen function, but with the same LP values, but different Q for eccentricity 0.5. Here are the changes from index from -100 to 100. Okay, so here orbits are objects on Hera orbits crossing. When they are crossing LEO, we have to take into account especially geopotential with high order and degree, and the atmosphere drag perturbation. When object crossing the MEO region, we have to take also geopotential, but with lower order and degree. We have to take also into account the lunisolar effects and solar radiation pressure. And when objects crosses geo regions, we're taking the geopotential with low order and degree, lunisolar effects, and the solar radiation pressure. Here in the plot we can see the changes in position vector with and without the forces. Here is a first order short period perturbation due to J2. These are second order perturbation and the solar radiation pressure perturbation and the atmospheric drag perturbation. And this is for objects on which has the altitude of perigee about 400 kilometers. So we can see that the value, for example, here in atmospheric perturbation are reaching about 18 kilometers in 2 days. But for object which has the perigee altitude about 1,000 kilometers, for atmospheric perturbation, the influence of atmosphere is really weak, and the changes in 2 days reaches about 0.02. But the different objects has a different area to mass ratio, and there are non-gravitational perturbation here. As we can see, with different area to mass ratio value, the changes in this perturbation changes rapidly, because for example the red one, I don't know, it's seeable, red one here is the value of 0.02, and for example the blue line is 0.1. So it's changing, and if we have an object, sometimes we don't know its area to mass ratio, so we have to check for different values how it's changing the position vector. Okay, and for orbit propagation, we can get the mean elements, which is here written, here plotted with a green line, and it's quite stable, and the oscillating elements, which are changing for this exemplary object about 40 kilometers. In semi-major axis, also there are seeable quite big changes in the oscillating elements. Okay, so as a conclusion, we can say that there are more than 1/1500 objects with eccentricity above 0.4, and there are a huge threat for objects in each region on Earth orbits. And one of the reasons is because they've got really high velocity in their perigee. And we presented the effective methods for calculation orbits with high eccentricity value using modified Hansen coefficients, using analytical theory, and orbits propagation in oscillating and mean elements using the Mersmann transformation. Thank you.